So today's lesson, we're going to talk about the Standard Model. Now, the Standard Model isn't a complete refashioning of the model of the atom or of matter. It's more so an addition to what we thought was the classical construct of the atom and of matter as a whole. So in this lesson, we're going to start with assuming we have the basic knowledge of what the newest model in classical physics that you learned in chemistry class. So that's what I've placed below here, where we have neutrons and protons in the nucleus. So those are the nucleons, and we have the electrons kind of floating around in a shell or a cloud or whatever it is level of chemistry you guys discussed. Now, the Standard Model just takes all the new particles and mashes them in with the old particles and makes one kind of diagram explaining all of that, which is here. Now, before you start panicking, this is on your reference table, and we're going to walk through this together as we go. So this is the classification of matter chart. Now, matter is everything that exists in the universe, all this stuff in the universe. Now, there's two different categories. There's hadrons, which we're going to get into in a little while, and then there's leptons. Leptons are the ones we're going to talk about first. So leptons are any member of a class of subatomic particles that respond only to the electromagnetic force, the weak force, the gravitational force, but are not affected by the strong force. So, that sounds like a bunch of mumbo-jumbo, so let me just explain. The weak nuclear force. The weak nuclear force is the one that holds the protons and neutrons together to make the nucleus. That's the force that holds them together. Okay? The strong nuclear force bonds the atoms themselves, the quarks, together, which we'll get to later. So neutrons and protons, we're going to talk about in a little while, are comprised of even smaller particles. So those are going to make the force, the strong force is what glues those together. So leptons are not affected by that. Matter of fact, leptons have nothing to do with quarks. So the only of the particles that we're going to talk about today that don't have anything to do with quarks. Okay? Now, it's then goes on to say that leptons are said to be elementary particles, which means, as I just said, they don't appear to be made up of any smaller units of matter. So as of now, with the technology that we currently have, we don't believe that they get any smaller. There's any particles that make up these little subatomic particles. Now, it goes on to say they can either have one elementary charge or they can have zero charge. Now, what we see here is there's really two different categories of lepton. There's these, which are electron-like leptons. All right. And then there are these, which are known as neutrinos. There's three different types of neutrinos. This one is known as an electron neutrino because it has some characteristics that are very similar to electrons, but there's one major difference, obviously. This has no charge to it. This has a charge of -1. Each of these, same thing, have characteristics similar to their electron-like counterparts, but they're not electrons, they have zero charge. So, these are the electron-like particles, and these are the neutrinos. Now, the easiest way to remember that they're neutral or zero charge is that they start with neut, which is the same as neutral. Okay, so that's really, for this explanation, all you need to know about leptons. So now we go back to the chart, and we're going to talk about the next type of particle. So under the umbrella of hadrons, there's two different types of particle. There's mesons and baryons. So next one we're going to talk about is mesons. Okay, so meson is a subatomic particle which is intermediate in mass. So the leptons were the really tiny ones, the really high energy but really small particles. These are medium mass particles. Granted, these are still subatomic particles, so they're still tiny, 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 but they're somewhere between the mass of an electron, which is itty-bitty, and the mass of a proton, which in the atomic world is rather large. Okay, it goes on to say it transmits the strong interaction that binds nucleons together. Now, that's well above our pay grade for this class. So what I just want you to know is that they are particles that don't often exist on themselves, unto themselves. They exist kind of intertwined within the other particles that we're familiar with. And they really only ever come out and pop out individually by themselves in high energy explosions or interactions like fission, fusion, things like that. You'll see them, and even still, you'll only see them for short periods of time while they're kind of doing their job, and then they go back into hiding. So mesons, we could do an entire class, an entire graduate level class on just these types of particles. But mesons, that's really all you need to know about them. So now we have the last one, baryons. Baryons are probably, arguably, the most important to us because baryons are our meat and potatoes. Baryons are where, for instance, our protons and neutrons lie. So baryons are heavy subatomic particles that are made up of 3 quarks. So we're going to get into that in a second. I know it's been mentioned a couple times, but they're the biggest of the subatomic particles. So it also go on to say here, both protons and neutrons as well are baryons. So baryons are 90% of the matter that we see day in and day out are baryons. The other, or let's not say that. 60% of the matter we see from day in and day out is that. 39% of the rest of it is electrons, and then the 1% is all the other types of particles we've talked about. So, baryons are super duper important. Now, let's talk about quarks for a second, because it mentioned the idea that baryons, for instance, let's go back to the original chart. On the original chart, it tells you that a baryon is comprised of 3 quarks. So here's the thing where you may not have talked about this in chemistry class, and a lot of people don't know this, but protons and neutrons are not the smallest particles you can have. Each proton or neutron or any other subatomic particle is comprised of 3 quarks, or anything that's a baryon, anything that's in that category is comprised of 3 quarks, which are these tiny little string-like objects, which is where the term string theory comes from. Again, above our pay grade, outside of where we're going to go with this, but just in case you ever get asked on Jeopardy or something. Mesons, and I figured I told you I'd come back to this, are comprised of a quark and an antiquark, which will come back to the idea of an antiquark. So for now, all you have to know is that all the particles in this category are comprised of quarks. Okay, so tinier little particles that are significantly smaller than the ones that we've always thought are smallest. And they look like little springs or little strings. We'll get back to that. So, here's our chart of quarks. Now, they have odd names. Up and down, those are okay, understandable. Top and bottom, also understandable. Up, down, top, bottom have to do with what are known as spin, which we don't have to know other than the fact that it's something that exists with subatomic particles, and magnetic dipole moment, which again, you don't have to know. But that's kind of how we're able to differentiate between these different particles that otherwise look identical. For instance, looking at up, down, and up Charman's top, they all have the same charge. Now, that's the next thing I want to talk about. These charges have charges that are less than 1e. So right now you're all probably angry, saying, Mr. Austin lied to us. He said that you can't have a fraction of elementary charge. And that's true. On the macroscopic level, anything above the proton and neutron level, you can't. When you get to this wacky subatomic particle world, things kind of fall apart, because not only can you have fractional charges, but you can have irrational number charges. So 2/3 is a repeating decimal. So it's a very weird situation, but it can happen. Now, there are 2 sets of 3 with the same charge. So that's why you have to have this other information, because otherwise the up, the charge, and the top would be indiscernible between each other, because they all have 2/3 e a charge. They're all reasonably the same size. They're all so small we can't actually physically see them with the naked eye. So we had to have some other ways of discerning between the different ones. So we were able to look at their spin and a magnetic dipole moment to differentiate between the three. Same thing with down and strange and bottom, where each of them have a charge of -1/3. However, they all have different spins and or magnetic dipole moments. Now, how does this work? So I put a whole bunch of information out there. So all hadrons are comprised of a combination of quarks, right? So, for instance, a proton, one of the ones we're familiar with, is comprised of an up, and a down. Now, we just use the symbols, the lowercase letters, and you can even see here, I mean, if you see it on a test question, it's going to be italicized because they are here. But if you look, up, charm, top, down, strange, bottom. So they're just going to use those lowercase italicized letters to represent each one. So for a proton, I'm going to rewrite this because it just looks sloppy. We have, so a proton is an up, and a down. So that means that it's comprised of those three different quarks all kind of inside the proton. These little squiggly looking little particles all moving around and jumbling around. So that gets crazy when we start looking at those models. Now, here, question 2 or part 2 here, I just want to discuss with you the fact that this does still follow the classical rule, as do all subatomic particles. So all subatomic particles, protons, neutrons, all other hadrons, hint, hint, I'm saying this slowly for a reason, have charges that follow classical physics. So it's either 0e, 1e, or -1e. But it's the sum of their parts that add up to 1e, -e, or 0. So from that, what do I mean? A proton has an up. Now, looking at the charge, up is 2/3. So we got positive 2/3 E plus positive 2/3 E plus a down. A down has a charge of -1/3 E. So we got -1/3 E. So this is our up, and our down. So this should still adhere to classical physics rules. So 2/3 and 2/3 gives us 4/3 E plus -1/3 E. And then that adds up to be, well, positive 3/3 E, which is 1 E. Physics still works. Now, this also works with a neutron. A neutron is a up, a down, and a down. So very, very similar in its makeup. It's really just different by a down particle. And that's kind of where those mesons come into play, but we're not going to get into that. All right, so this is going to be positive 2/3 E plus -1/3 E plus -1/3 E. And if you look, -1/3 and -1/3 give you -2/3. -2/3 plus positive 2/3 is 0 E. And all is right with the world again, because we know that neutrons have 0 E of charge. Okay, so I threw a lot of information at you so far. So what do you need to know? Looking back at this chart, you need to know that matter is broken up into 2 categories, hadrons and leptons. You have to know that the leptons are high energy. You have to know that they are indivisible. So they can't be broken up into any smaller pieces. They are elementary particles. They are the smallest they could possibly be. Okay, hadrons are the other particles, and they are broken up into 2 separate categories. Mesons, which are, another thing I should have put in here, very low mass. These are virtually massless. These guys are kind of medium mass, medium energy, which Me, medium, meson, and they are comprised of a quark and antiquark. I haven't forgotten about that yet. I just wanted to kind of sum up what we've talked about thus far. Okay? So you can even see by size, this is comprised of 2 of these little quarky-like particles. These are comprised of 3. So obviously this guy is bigger than this guy. Now, baryons are your large, relatively stable, or, excuse me. These are large and relatively stable, or low energy, not super high energy particles. So in the grand scheme of things, these are like Papa Bear, these are like Mama Bear, and these are like Baby Bear, right? I know I've been reading a lot of stories to my daughter lately, so forgive the analogy. All right, last thing I want to talk about is this, because it sounds very science fiction-y, but it's really not. So antimatter. Every type of elementary and subatomic particle has an antiparticle that has the opposite charge when applicable, and I'll talk about that in a second, and the opposite spin and magnetic moment, which I talked about before, and I still continue to say is above our pay grade. So why do I have to bring up that spin and magnetic moment part? Well, let's say a neutron, right? So you have a neutron. A neutron has a charge of 0 e. There is such thing as an anti-neutron, which in order to write it anti-neutron, they have a really easy kind of writing system where you just put a little bar over the top. So this is an anti-neutron. Well, there's no such thing as anti or opposite of 0. So this still has a charge of 0 e. However, it would have an opposite spin and an opposite magnetic moment from a regular neutron. Okay. Now, there are other examples that you should know. For instance, an electron has obviously a charge of negative 1 e. An anti-electron is known as a positron. They sometimes write this as E with a positive instead. And this obviously has a charge of positive 1 e. Now, there is such thing as a antiproton. An antiproton is comprised of, you guessed it, oh, no you didn't, because I just wrote that wrong, an up, an up, and a down, but it's technically an anti-up, anti-up, and anti-down. So even quarks have associated anti-quarks, which when put together make the associated anti-particle. So an anti-up, and an anti-down make an antiproton, okay? Which I'm sure in the nuclear physics world has a fancy name, but we're not going to give it that. We're just going to leave it as antiproton. We are going to point out the fact that it has a negative 1 e of charge, which, if you wanted to go through and talk about mathematically why that's the case, well, if I come over here, up has positive 2/3. So anti-up would have negative 2/3. All right? This would also be negative 2/3. And an anti-down would be anti the negative 1/3 it had before. So this would be positive 1/3. Right? So we got negative 4/3, gives us negative 3/3, which is just negative 1 e. Now, you're probably saying to yourself, what the heck? Why did we never learn about this stuff? Why don't we just see these things floating around? Why we never talk about anti-helium or anti-uranium or anti-oxygen or anything like that? Well, let me explain why. The second paragraph and kind of the third paragraph explain why. The reason we don't see these in everyday life is because when they come into contact with their matter counterpart, they annihilate. We will talk about that in more detail, kind of what comes of it, specifically what comes of it when they annihilate. But the simple answer is, if I have a proton, so if I have Mr. Proton here, and I have Mr. Antiproton here, and they run into each other, which if they're in the general vicinity of each other, they're going to do very quickly, or they're going to want to do very much, because remember, this guy has a charge of positive 1, this guy has a charge of negative 1, which means they're attracted to each other. But when they run into each other, boom, they annihilate. So basically what that means is they just disappear, seemingly disappear, but they really just become pure energy. Okay? So this is why we don't see these particles very much in the real world, because if we had, let's say you had a cup of antimatter, anti-water, and you poured it into a cup of not anti-water, regular water, it would explode tremendously and it would probably level your city block. All right? So that's why antimatter is not something we see very often. There are many reasons. There's actually a good video that I can point you in the direction of if you want to know about it. But there's actually a very good video, which I might actually send a post out on the Google Classroom anyway, explaining why, when it came time, or at the very beginning of time after the Big Bang, why it is that matter won out over antimatter. Because antimatter, I guess, just could have one would argue that antimatter could have just as easily been what everything is made of, and that matter could have been the one that kind of fizzled out to nothingness. But there's actually a good little video on it, which I'll post the link to. It's a YouTube video when we're done with this. But what you did notice, hopefully, about this is this whole topic is very qualitative. All right? There was a lot of information presented, so as you're going through the questions in your assignment, you may want to go look back at the questions, or go look back at the video. I tried to put a lot more text in here and a lot less speaking, because this way, if you don't want to listen to me talking, you just want to fast forward through to the different sheets and different slides that I put on here. Any information you're going to need is on here, or it's on your reference table. All right? So good luck with the assignment. It shouldn't be too terribly difficult. I assure you this is the harder of the two topics this year. The next topic, this week rather, the next topic next Wednesday, which is going to just kind of wrap everything up in a nice bow. It's going to basically talk about this in more detail, and it's going to talk about Einstein finally and his E equals mc squared. But long story short, very qualitative concept. We're not going to do a lot of numbers involved, although you really should, just to give you an idea, be able to do this stuff, and you should remember this idea that the amount of charge can only be, or that some amount of charge of something that's labeled as a subatomic particle can either be 0, -1e, or +1e. If it comes out to be a fraction, classical physics is still right, and it still doesn't count. All right? So I will talk to you guys soon, and I hope this lecture worked for you.